We can solve any linear congruence provided the greatest common divisor of the coefficient of x and the modulus is 1. What about congruences like, or in general, f of x congruent to d mod n, where f is a polynomial of degree n? The simplest case is when f of x is some power of n, so we're trying to solve x to the power n congruent to a. By analogy with the situation for real numbers, if x to the n is congruent to a mod n, we say that x is an nth root of a mod n. For example, let's try to find x cubed congruent to 29 mod 37. So remember, trial and error always works, and since we're working mod 37, we only need to try out the values from 1 to 36 and see if any of them work. And so we find now, as our modulus gets larger, this becomes more difficult, so is there a way to avoid trial and error? In general, no. However, in some cases we can. Remember that for any modulus n, and greatest common divisor of a and n being 1, the Euler-Fermat theorem guarantees a to the power phi of n is congruent to 1 mod n. In some cases, this allows us to calculate the root directly. For example, suppose we know x to the fifth is congruent to 78 mod 85. So we can compute phi of 85. 85 is the product of two primes, 5 and 17, and so phi of 85 is a product of phi of 5 and phi of 17, and since these are both primes, their phi values are prime minus 1, and so phi of 85 is 64. So x to the power 64 is congruent to 1 mod 85, and this means that x to the power 65 is congruent to x. And the important thing about that is 65 is 5 times 13. So if we raise both sides to the 13th power, we'll find x. And so raising both sides to the 13th power gives us our left-hand side is x to the 65. Our right-hand side we can compute. Since x to the 64 is congruent to 1, then x to the 65 is congruent to x, and that gives us x congruent to 28, which is our solution. Let's try that for x to the fifth congruent to 16 mod 23. We have phi of 23, well that's prime, so that'll be 22. So x to the 23rd is congruent to x. But we can't raise x to the fifth to a power to get x to the 23rd. But since x to the 22 is congruent to 1 mod 23, it's also true that x to the 44th is congruent to 1, and that means x to the 45th is congruent to x. And now, if we raise both sides to the 9th power, we'll get x to the 45. So raising both sides to the 9th power gives us, and this allows us to compute x directly. This suggests the following approach. To solve a congruence x to the n congruent to a, find phi of n, then find a k so that nk is congruent to 1 mod phi of n. So raising both sides to the kth power will give us x to the nk congruent to a to the k, but since nk is congruent to 1 mod phi of n, then x is congruent to a to the k. And this works in many, but not all cases. So we've seen a couple of cases where it does work. Let's take a look at one where it doesn't. We want to solve x to the fifth congruent to 33 mod 31. We find phi of 31 is 30, and so x to the 30th is congruent to 1, x to the 60th is congruent to 1, x to the 90th is congruent to 1, and so on. And that means if we raise things to one higher power, then we get x. But these are all multiples of 30, and since the greatest common divisor of 5 and 30 isn't 1, we can't raise 5 to a power to get an exponent congruent to 1 mod 30. So we have to use trial and error, or something else.